Hello friends, in this video I am going to discuss the unit structure of atom for NEET preparation. I have chosen some of the previous year's NEET exams questions. To begin with, I have a question on board. Let's see this. 4d, 5p, 5f and 6p orbitals are arranged in the order of decreasing energy. The correct option is. Let's solve this. To solve this question, we must know a rule called N plus L rule. N plus L rule. For any two orbitals, if we calculate N plus L value, if one of the orbital has greater N plus L value, that orbital will have greater energy. Also, if two orbitals have same N plus L values, in such case the one with greater N value will have a greater energy. Based on this rule, we have to find out which is the right option. Okay, let's take it. First one is 5f orbital. Now I want to calculate N plus L value for this. N is the principal quantum number which is given by the number in the representation. So it is 5 plus. L value is obtained from the symbol, orbital symbol F here. For your information, the L values of S, P, D and F orbitals are 0, 1, 2, 3. These things we have seen in quantum numbers. So now I will substitute the value of F here. This will be equal to 8. Now the second orbital given is 6p. 5f, 6p. 6p for this, if I calculate N plus L, will become 6 plus 1, 7. The third orbital given is 4d. Again I will calculate N plus L, which is 4 plus d is 2, which is equal to 6. Finally, we have 5p orbital, for which I will calculate N plus L as 5 plus 1 equal to 6. Now we have got all the values of these four orbitals. The decreasing order we want, it is given in the question, decreasing energy. So highest energy is possessed by 5f orbital. I'll take 5f first. This is greater than, next is 7, which is 6p, which is greater than. Next orbital, we have got 6 and 6 for both orbitals. In such case, the one with greater N value will have greater energy. Therefore, 5p comes and finally 4d. This is the decreasing order of energy for these orbitals. Now have a look at the options given. Whichever is matching with this is the right answer, and it is option B. 5f greater than 6p greater than 5p greater than 4d. For any such question, you have to find out N plus L value and find out the right answer. Now let's take question number 2. Which of the following series of transitions in the spectrum of hydrogen atom falls in visible region? We have four options. In hydrogen spectrum, we have got different series of transitions, and we have named those by the names of different scientists. To remember that, there is an easy way. The series are remembered like this: L, B, P, B, P. Okay, where L is Lyman series, B is Balmer series, P is Paschen series, again B is Brackett series, and finally P, Fund series. So these are the different series of lines seen in hydrogen spectrum. For these series, let us remember the values of N1 and N2 also. Lyman will have value 1 and N2 can be 2, 3, 4, etc. Balmer will have N1 value 2, N2 will have 2, 3, 4, etc. In Paschen, N1 is 3, N2 is 4, this is 3, 4, 5, etc. This is 4, 5, etc. And bracket will have n1 value 4, n2 value 5, 6, etc. And find values are n1 equal to 5 and n2 equal to 6, 7, etc. Definitely n2 will have one number greater than the n1 value and more. Apart from this, we can also remember one more thing, that is in which region the series of lines fall in hydrogen spectrum. Lyman series falls in UV region, ultraviolet region. Balmer falls in visible region. Paschen series IR, IR and IR. Why all these three are in IR region only is because the difference in energies from the fourth level onwards will be reduced. The gap is not so much. So all these series fall in infrared region only. Whereas we would say near infrared, mid infrared, far infrared. Alright. Now the question is, which of the following series in spectrum falls in visible region? So the answer is, in visible region we can see the Balmer series. This is option C, Balmer series. Now let's take question number 3. Orbital having 3 angular nodes and 3 total nodes is. We have got the 4 options 5p, 3d, 4f and 6d. Okay. Let us understand first the 2 different types of nodes. The first is radial nodes. The number of radial nodes is given by n minus l minus 1 and number of angular nodes is given by L, simply L. Then what happens to the total number of nodes? Total nodes is equal to, just cancel L and L, you will get n minus 1. So this is total number of nodes and this is only angular nodes. Now verify the options one by one. Option A is given as 5p. I am considering once again the orbitals S, P, D, F, which we have seen in our first question, 0, 1, 2, 3. Okay, substitute the values. We want angular nodes. So angular nodes is equal to L and that's equal to, since it is P, P means 1, which is 1. And we want total nodes also. Total nodes are given by n minus 1. N is 5. Minus 1 is 4, but we want 3 angular nodes and 3 total nodes. So option A is over. Option B, 3D. For 3D orbital, angular nodes is equal to L. L is D, D is 2. Of course, the answer is wrong again. Anyway, total nodes is equal to n minus 1. If we do n minus 1, 3 minus 1 will become 2. Again, wrong answer. Option C is 4f. For 4f, angular nodes is equal to L. L for f orbital is 3. So I got 3 here. Then total number of nodes is n minus 1, which means 4 minus 1, 3. Yes, we got our answer, option C. Anyway, I will verify the D option also, which is 6D. For 6D, angular nodes is equal to 2, since the orbital is D. Total number of nodes is equal to 6 minus 1, 5. So our answer is C, 4F. Angular nodes are 3, total nodes are 3. Okay, have a look at the other question. Question number 4. In hydrogen atom, the de Broglie wavelength of an electron in the second Bohr orbit is. The Bohr radius is given, A0 is equal to 52.9 picometer. Now we have to find out the de Broglie wavelength. Okay. De Broglie wave equation is also called matter wave equation, is given as lambda is equal to h by m into v. h is Planck's constant, mass of the particle, velocity of the particle. But we have got the radius value given. Using the radius value, can we find out the term h by mv is the point here. Anyway, in Bohr's theory, we also have seen that mvr is equal to nh by 2 pi. This is the law of conservation of angular momentum for an electron according to Bohr's atomic theory. Now, using this expression, can we derive the value or the point for lambda, expression for lambda? Let's see. Rearrange the terms here. You will get h by m into v equals, so m and v have gone to RHS, I get 2 pi r by n. So I have this equation here where I can equate this to lambda. So now I can calculate the lambda value using this expression 2 pi r by n. Anyway, I don't know the value of r because this is a0, the radius of first orbit or first Bohr orbit. I want the second Bohr orbit value. So I first calculate the second Bohr orbit value, where we have the equation an equals 52.9 into n square picometer. This is the expression to find out the radius value. Okay, if I substitute n equal to 2, because this is second orbit, I put n equal to 2, so that 52.9 into 2 square will be, into 4 it will be. So now I will calculate into 4. I got 211.6 picometer. This is the value of A2, second Bohr orbit. Okay, now I will substitute everything here to get the value of lambda. Therefore, lambda is equal to 2 pi. R is 211.6 over n is 2, second orbit. So 2 got cancelled. My final answer is 211.6 pi picometer. This is in option B, 211.6 pi picometer. Now let's take question number 5. How many electrons can fit in the orbital for which n is equal to 3, l is equal to 1? A little tricky question, I believe. Let's see. If n is equal to 3, we know that l values can be 0, 1, 2. Now the question is, how many electrons can fit? Let us say, if l is 1, the values of m are -1, 0, +1. This is how we used to write the orbitals from the data given for n and l. Now these three values represent the three orbitals of p orbital, namely px, py, pz. Okay. The total number of electrons that can fit in these three orbitals will be 1, 2, 3, 4, 5, 6. Rather, fill all the three orbitals first and then start pairing. Okay. Now there are 6 electrons possible for the values n equal to 3 and l equal to 1. But the question is, how many electrons can fit in the orbital? It is only in one orbital. In a specific orbital, if you observe, how many electrons can fit in one orbital is the question, not how many electrons can have the values n equal to 3 and l equal to 1. So usually students get confused thinking that there are 6 electrons possible and they mark it as option B. But the right answer is option A, only 2 electrons can fit. Even though if they have not mentioned any detail, we can easily say that one orbital can hold only 2 electrons always with opposite spins, +½ and -½. So the right answer is option A, 2 electrons. Let's take question number 6. Which of the following pairs of d orbitals will have electron density along the axis? So this is about along the axis. We know that d orbitals have a set of 5 degenerate orbitals. 5 degenerate orbitals, that is equal energy orbitals. Each orbital is indicated by the symbol dxy, dyz, dxz, dx square minus y square, and finally dz square. If we see the distribution of electron density in these orbitals, there are 3 such orbitals where the orbital lobes are directed between the axes, and 2 other orbitals have their electron density or lobes distributed along the axis. So xy will have a representation like this, x and y. It is a double shape which has its lobes directed between x and y axis. Similarly, yz also, between y and z. Between x and z, we will have dxz. Whereas dx square minus y square will have its orbitals directed along the axis, x axis and y axis. This is dx square minus y square, and dz square has maximum density, electron density along z axis, like this. So the right answer among the given options is option C, dz square and dx square minus y square. These 3 orbitals have their densities between the axes. Okay, question number 7. The number of d electrons in Fe2+, which is called ferrous, is not equal to the number of electrons in which of the following? Okay, we have all these 4 options. Let us verify first. This is given as Fe2+. For your information, there is one easy way to remember the configurations of 3D series elements starting from scandium to zinc. If you just remember these 10 elements, you can write their atomic number and configuration with respect to the atomic number easily. Like scandium has atomic number 21, and I'll consider iron also. Iron has 26. Look at the numbers 2, 1. Just write 4s and 3d. 4s will have 2 electrons, 3d will have 1 electron. As the atomic number is given, the same way you have to write the configuration. Except for those 2 elements, chromium and copper, where we say 4s1 3d5 for chromium, 4s1 3d10 for copper. Otherwise, the rest of the elements follow this. It is 4s 3d, say 4s2 3d6, like this. Okay, now I will consider the first case, that is scandium with atomic number 26. Okay. If iron is 26, its configuration is argon core 4s2 3d6. Now since this is Fe2+, I have to remove electrons, 2 electrons from 4s orbital, and therefore I have totally 6 electrons in the d orbital. This is the d electrons in Fe2+. Now the question is, in which of these 6 electrons are not present? D electrons of iron, once again it will be same, 3d6 only, so it is equal. P electrons in neon with atomic number 10, so I will consider neon, atomic number 10, 1s2, 2s2, 2p6. Now P electrons, how many are there? You can see 6 electrons, which means it is also equal. Option C says S electrons in magnesium, so I take magnesium, atomic number 12, written as 1s2, 2s2, 2p6, 3s2. Look at the s orbitals. There are totally 3 s orbitals, each having 2 electrons, equal to 6 electrons. Done. Finally, p electrons in chlorine. Chlorine has atomic number 17 and configuration is given as 1s2, 2s2, 2p6, 3s2, 3p5. Now look at the number of electrons in P. 2p has 6 electrons, 3p has 5 electrons. Totally there are 11 electrons in p orbitals of chlorine. So this is not same as that of Fe2 plus ion. Therefore option D is the right answer. Okay, now have a look at this question. Calculate the energy in joule corresponding to light of wavelength 45 nanometer, and they have given the value of Planck's constant. Okay, let's solve this. We want energy value, which is given as E is equal to h nu, Planck's equation. Alter this for nu, you will have hc by lambda, because wavelength is given and c is known for us and h is given. This will give you the right answer. Okay. In most of the times, such questions will be based on finding 10 powers accurately. So if you know the exact power of 10, 99% of your answer is okay. So let's see. H value is 6.63 into 10 power minus 34 into speed of light is 3 into 10 to the power 8 meter per second, standard unit. Lambda is given as 45 nanometers, so I'll take 45 into 10 power minus 9 meter. Alright, now do the calculation. It is simple. This is 315 times is 45 and 15 6.6. 15 4s are 60, which means I have 1 point here. Just take it here. It will be 0 point. So 0.4 something into 10 to the power. There is minus 34, and in the denominator minus 9. If it comes to numerator, becomes plus 9. So we have 10 power 8 into 10 power 9, 10 power 17. Minus 34 and plus 17 gives you 70. Okay, of course minus. So into minus 17 joule will be the answer. But we don't have that. Anyway, this is 0.4 something. Definitely the answer must be 4 point something into 10 power minus 18 joule. So that value is in option D. 4.42 into 10 power minus 18. You need not find out the exact answer, because you may get some hint in the answer so that you can relate it to one of the options. But finding 10 powers is most important in such cases. I hope you followed all these things. Now have a look at the solution. Okay, that's all for this session. In my next video, I am going to solve some more questions of the same unit, structure of atom. Keep watching. Thank you very much.